Okay, now I'm going to start working some Hardy-Weinberg problems. In our first situation, it says in flowers, red color is dominant over white. In a certain population, there are 75 red and then 25 white plants. Hopefully you're thinking to yourself, well, the 75 red, they can either be red by being homozygous dominant, or they can be red by being heterozygous. So since I can't determine which of these are homozygous dominant versus heterozygous, I'm going to start with the white plants. You know the white plants for sure have to be homozygous recessive. And going back to our variables, Q squared represents our homozygous recessive individuals. So for this problem, Q squared is going to equal 25 out of 100. 100 being our total, 75 plus 25 is 100. I'm going to write that as a decimal so that I get Q squared equals 0.25. Okay? To find Q, which would be the frequency or percentage of the alleles that are recessive, I'm just going to square root both sides. So square root Q squared to find Q. If I take the square root of 0.25, that's 0.5. How did I figure that out? I'm thinking 0.5 times 0.5 equals 0.25. Okay, they're perfect squares or perfect square roots. Okay, my first Hardy-Weinberg equation that I learned was P plus Q equals 1. So hopefully you're seeing how easy this is. If Q is 0.5, 1 minus 0.5 will give me my P. So the percentage of the alleles that are dominant is also 0.5. So in this particular situation, I have half of my alleles that are dominant and half of the alleles are recessive. Now this problem doesn't ask me to, but I'm going to go ahead and show you how I would figure out what percentage of the population was homozygous dominant. I'm going to abbreviate. What percentage of the population was homozygous recessive? And finally, what percentage of the population was heterozygous? Okay. My second Hardy-Weinberg equation that I need is P squared plus 2PQ plus Q squared equals 1. Okay, I'm going to use that second equation to figure out these three categories. Remember, the percentage of the population that is homozygous dominant is P squared. The percentage of the population that is homozygous recessive is Q squared. And then the percentage of the population that is heterozygous is that full term 2PQ. Hopefully you see that the Q squared is what they were giving us in the question with your 25 white plants. So that's going to be 0.25, or I could think of that as 25%. P squared, I need to take the P. The percentage of the alleles that were dominant, that was 0.5. 0.5 squared is also 0.25. So in this particular scenario, I have an equal amount of individuals that are homozygous dominant and homozygous recessive. Okay, our last category for the heterozygous individuals. There are two different ways I can think about solving for this last category. I can either go back to this equation and I can plug in 2 times P times Q. So that would be 2 times 0.5 times 0.5. I can do that math and it would get me the answer. Or I can think about the fact that I have two of these categories. I've already calculated the P squared and the Q squared. And if the three categories add up to 1, and I know two of them, I can do 1 minus the P squared minus the Q squared to leave me my third category. In other words, 1 minus 0.25 minus another 0.25 would give me a value of 0.5 remaining. These three genotype combinations must add up to my full population of 1 or 100%. Okay, so that's the first Hardy-Weinberg type of problem.